I'll start the recording though, so we can get going since it's 12:33. So we have a new lecture to start today, new unit, on generalized models, and I posted just this morning and sent out an email about it, an example for categorical outcomes. So this handout has binary outcomes, ordinal outcomes, and the online materials have nominal, but I did not include that in the handout because I didn't think that we would end up having time to go over it. As a reminder, your next formative assessment due Monday. After today, you should be able to answer all of it, and then a week from Monday is homework 4. So let me know if you have questions as you get into it about what you should be doing or strategies. Just want to remind folks that it doesn't have to be perfect. It needs to be at least 3/4 complete with respect to the points attempted. That's all. If you're stuck on something, if you're not sure what to do, or if you need help, like you start writing it up and you realize you don't understand something or you don't know how to do something, you can put comments like in the document for me and we can have a conversation about it. So this is just a first draft, essentially, is the way to think about it. I'll give you feedback on it, and you get a chance to revise it for up to full points and turn that in by the end of finals week. If you get your homework back from me and you're like, this is good enough and I don't have time to make it perfect, good for you. Knowing when to say when is an important skill because we can't do everything perfectly all the time. So if you're happy with whatever you get the first time, you don't need to revise. If you're not happy, then you can work on it some more. Sound good? All right. I don't know how to cry, Uncle. Oh, you got to learn though. You got to learn. You'll see a couple examples of that in my handout where I couldn't figure something out in R, and it just says this didn't work, but it should have, and that's where I landed because I just at some point you got to just stop. You know, nothing's going to be perfect.
I mean, unless you're okay having mental breakdowns.
Yeah.
Like all the time.
No mental breakdowns.
Like, if that's the life you want to lead, then by all means,
yeah,
keep striving for perfectionism.
Perfectionism is not good. I listened to a podcast called The Academic Imperfectionist. It's this philosopher from London, and I really love her voice. But she talks about this sort of issue of how to live a balanced life and not let things overwhelm you and all that stuff. She's very good. I would recommend it. Did you get candy?
No? Oh
okay, yeah. Come get some candy. And if you are just sitting here and you're like, I really could use another piece of chocolate during class, just come on up and get it. It's fine. All right, so we got that. We have lecture 6. Are we ready to do this?
Yes.
Okay. So for those of you who have had coursework in generalized linear modeling, including from myself, I teach that course every spring. We'll be teaching it this spring as well. This will all look very familiar. If you haven't had coursework in this area, then this will look strange and complicated. So I understand that. We're not going to do every generalized modeling variant that there is. I'm going to focus on sort of 2 families, categorical outcomes, and then I'm going to build an example for count outcomes, and the other ones would follow logically from this. So we don't have to do all of generalized models. Fortunately, most of what you've already learned follows straightforwardly. There's just a few things that go a little bit sideways when we start to predict outcomes that aren't normal, pseudo R-square being the first thing to go. Also, estimation becomes much more complicated, and so I want to talk a little bit about why that is. So, all right. Away we go then. First thing, words. Clarifying terminology, because the way that we talk about models in terms of predicting not normal outcomes is a little bit different, and I want to tell you about why. So, the variants that we've seen so far all fall under the heading of general. Even though that word seems like it should mean general, it actually has a very specific meaning. General means residuals that are normal. And another way to say that is conditionally normal. And in multi-level models where we have multiple piles of variance, because we have multiple dimensions of sampling, there are 2 different types of residuals in what is known as the G matrix. So this is coming from the lecture that I recorded while I was at the conference, if you had a chance to watch that. We didn't talk about it in class. We have variances and covariance of the level 2 random effects. So some people call those level 2 residuals because after you start putting level 2 predictors in, they also become left over, but I tend not to use that word. But level 2 random effects are always assumed to have a multivariate normal distribution. And that is baked into every software package. Like, you have to work really hard to change that. And simulation research has suggested that that assumption doesn't matter as much because U's are not observed. So there's less of an impact of having a distribution that doesn't quite match. Our matrix is what is known as level 1, and what we've been talking about, level 1 residuals. So that's within cluster variation. Those are assumed to be multivariate normal as well. And in our models, because people are viewed as exchangeable within a cluster, there's no correlation structure that is relevant. So we don't ever do anything with respect to the level 1 residuals other than let them have a variance. And our models thus far have assumed constant variance for that. In the longitudinal class, there's a whole bunch of other things that we would do when we're talking about occasions rather than persons as level 1. So let's say that we have a model that looks like this. So we have a level 1 predictor that's been within cluster centered, cluster mean centered. We have a level 2 predictor that is the cluster mean, and the level 1 predictor has both a fixed slope and a random slope. So what this model would look like in terms of these matrices of random effects and level 1 residuals, at level 2, we have the variance of the intercepts right here, the variance of the within cluster X slopes right here, and the covariance right here. So I had a question in office hours the other day about why it is that when you add a random slope to the model, the change in degrees of freedom is 2 and not 1. This is why. Because we're adding this new variance, but we also add the variance of the random effect, covariance, of the random effects that were already there. So anytime you add a new random effect, you're adding both its variance and covariance with the things that were already in the model as random effects. At level 1, this would be like if we had 4 people within a cluster. We have a residual variance that is assumed to be constant across people and no covariances because people are supposed to be conditionally independent. That means people are not independent, but they are after you control for what cluster they're from and the random effects that go with that cluster. So conditionally means after controlling for stuff, what's left over. Okay, am I talking fast? I feel like I'm talking fast. No? Okay, well, Zoomers, I'm all right? Okay, I'm down to 7-Up. That just tells you how much caffeine I've already had today. So I've cut myself off. This scariness right here is this, if I try to write it out in terms of matrices. So if you look at textbooks and technical documentation, they might present this same model using matrices this way, where we have Y as a matrix that holds the answers, X is a design matrix, as it is sometimes called. It holds the predictors that have fixed effects. My notation here is consistent with the gamma, so this is a gamma matrix that holds the actual fixed effect estimates. Z is a matrix that holds the predictors that have random effects, so a column of 1 for the intercepts and then whatever values for X these people have. U holds the random effects themselves, and then E holds the residuals. So then, the model implied pattern of variance across people from the same cluster is built from this thing. So we have what is known as V is when you put it all back together again. Like, what is the distribution of our outcomes? It's V. That comes from the level 2 part, which is the first 3 terms here, added to the level 1 part. So Z controls what values of predictors a given person has within a cluster, so it's cluster specific and person specific. G is the variances and covariances of the random effects. Then we have to multiply it by Z transpose to make it the right dimensions to add to R. So this is how you would see the exact same things we've been talking about all semester from a different perspective. Like if you were in biostat or stat, this is what they would tell you about from this perspective. The reason I'm telling you about it is to introduce the idea of marginal versus conditional as a new vocabulary word. So marginally, we can use V because at level 2, the variances and covariances in here, these are supposed to be multivariate normal, the random effects are. In R, this is supposed to be multivariate normal, and when you stack it all together, following this equation, then V is multivariate normal. If you just focus on the conditional part, the level 1 part, then that would be written like this instead, where the fixed and random effects contribute to the mean of the outcome, and what's left is over here, just the level 1 residuals. And when we're talking about outcomes that are supposed to have normal residuals at both levels, we can talk about the marginal distribution of Y or the conditional distribution of Y, because they're both multivariate normal. So if I have a multivariate normal level 2 and a multivariate normal level 1, I can stack them together and the whole thing is. And that makes estimation really straightforward. So when you run these models like in homework, it takes a split second for something to come back. If you have a large database, it takes maybe a few seconds to come back, but it's very quick and easy because the whole thing can be fed into the multivariate normal distribution to figure out the height of each cluster given the predictor values and the parameters from the model. So conditional is the idea of leftover. After fixed and random effects, what's left over at level 1? So up to this point, I always talk about level 1 residuals. Like this is the level 1 residual variance, this is how much of the variance the predictors explained, and so forth. From this point forward in the generalized unit, I'm going to use the alternative terminology conditional distribution because level 1 residual really only works with normal outcomes. Conditional is the preferred term. So then the question is, if you're dealing with an outcome that's not continuous, like if you have binary outcomes, what kind of distribution should they follow? Well, every type of variable has a distribution that goes with it. Residuals that, how do you say this? Binary outcomes have a Bernoulli distribution, for instance. Nominal and ordinal outcomes have a multinomial distribution. Count outcomes can have like Poisson or negative binomial or all the sorts of other ones. So we're going to use the word conditional to describe what is the distribution of our outcome after we factor out the random effects and the fixed effects. It doesn't mean that there's no residuals. It doesn't mean the model is perfect. It just means that we don't talk about it that way. So, key idea, conditional, after fixed and random effects. That's what that means. Okay. So then terminology. Other ways that people will talk about these same things from the framework of mixed models rather than multi-level models, we have progressed all the way to the box number 4 here. So we're still in the world of mixed effects models, meaning that we have fixed effects and random effects. We need both if you have more than one dimension of sampling. But now we're adding on the ized part, where the term generalized means some kind of not normal outcome is being predicted. So we have to change our model with respect to the conditional distribution being not normal, and we also need to make sure that outcomes that are bounded, that have predictions that stay within those boundaries. So ized is the new terminology here. So in generalized models, we are predicting the mean still. So we have the model for the means. The only catch is that we're not predicting the outcome directly. We're predicting some transformation of it so that we can use the same kind of linear model that we have been up to this point. So the level 1 conditional model is going to change its distribution. So we'll switch it to Bernoulli or multinomial or something like that. Level 2 stays multivariate normal. And the slides that I have to start with this are single level slides. So just I for a subscript, like as if this were a cross-sectional sample with no clustering. Then we'll add on the multi-level part after we get a handle on just the generalized part. So most not normally distributed outcomes have some kind of like built-in model that you can order up to fit and predict these outcomes. So if you have categorical outcomes, meaning binary, ordered categories or ordinal, or nominal categories, there's models for that. There's models for counts. There's models for outcomes that are called censored, where there's sort of like a pile at one end because you couldn't measure them any further. Ceiling and floor effects work that way. Zero inflated, so if you have counts or amounts where there's a whole bunch of zeros, way more than you would expect based on the distribution. And then models for continuous things that are skewed, like response time or annual income, housing prices, that kind of stuff. So there's 3 parts to a generalized model. The big one, not normal distribution of y. The question is, if something is not continuous, what is a distribution that matches it better? So general models use a normal distribution. The variance is assumed constant because in the normal distribution, there's only one variance. That's why we have the assumption of normality and constant variance. Those 2 things go together. But if you have outcomes that are not continuous, then other distributions are going to be more plausible. I note that in the categorical textbooks that are written by Agresti, He refers to this aspect of conditional distribution as the random component, but he does not mean random effects. Unfortunately, there's an overlap in terminology there that's confusing. Why do we care about this? To get the right standard errors. What type of distribution you have dictates how your standard errors are formed, and so if you pick the wrong one, those are going to be off to some extent. Particularly for outcomes where the variance needs to change as a function of the mean, because as you get closer to a boundary, the variance is going to shrink. So if you don't have that taken into account, your predictions are going to be sometimes more variable than they should be and less variable than they should be in others. So not constant variance leads to not constant standard errors. This new thing in the middle here, this is your formative assessment last question. What's a link function? A link function is something you would never hear about unless you're in the world of generalized models. It is a transformation, but you're not transforming the data. That's the tricky part. That's a common misconception. What is happening is that the mean to be predicted, so the conditional mean as it's called, is being transformed into something that is unbounded. That way our linear model can be applied as usual. So link is the transformation to go from the data up to what the model is going to predict. To go back down again, that's known as an inverse link. And we'll see lots of examples of those. So as one, the obvious one that we'll start with, because it's the easy place relative to some of the other choices, binary. If you have a 0 or 1 outcome, what is the mean of a binary variable?
Proportion of 1.
Proportion of ones, right? It's actually the same formula. We just call it the proportion of ones to sort of a shortcut. So what that ends up being is a value that ranges between 0 and 1, and we would interpret the mean as the probability of getting a 1. So if you don't know anything else about a person, let's say 60% of your sample gets 1s, you would guess a probability of 0.6 that somebody would have a 1. And as you add in predictors, you're refining that probability, maybe bumping it up or bumping it down, but it needs to stay between 0 and 1. Well, if you fit a linear model, it's not going to. It could predict probabilities of 1.2 or negative probabilities. So the link function ensures that that doesn't happen. What we're going to do is change the probability into an outcome that is continuous via the link function, so that when we back transform the predictions from that link function, the predicted probabilities stay between 0 and 1 as we want them to be. So it's a trick. It's a really cool trick, but it's a trick. Same thing happens for, say, count outcomes. If I asked you, how many pieces of Halloween candy did you have today? What's the smallest amount that you could say? 0. You can't have negative counts. So if you want to try to predict a count outcome, you have to make sure that the predictions don't go negative. Otherwise, it doesn't make any sense. Well, to do that, we need a different link function, and usually we would use the natural log, because when you log something, it stays positive. And all of the models that you already know from this class and other classes on standard regression, those are technically nested in this framework if you think of what we're doing as using an identity link, meaning times 1. Like we're not transforming it because we don't have to. If we assume our outcomes are continuous, then we don't have to worry about our predictions going out of bounds because there are no boundaries. These models are relevant when you have an outcome that has 1 or more boundaries, either upper or lower or both, and you want to make sure your predictions stay within bounds. That is what a link function ensures happens. Okay, linear predictor then, that's the normal part. Once you accept the fact that you're picking some other conditional distribution based on what possible values your outcome can take, and once you introduce a transformation to make sure that your linear model can keep going, but when you back translate it, it stays within the boundaries, then we can use the exact same models that we're already using. So linear predictor is the term that gets used for this, and it includes both fixed effects and random effects to it. So that's why I have the blue in here, because the distinction of fixed versus random gets a little bit blurry. Both of them are considered part of the linear predictor. So we can talk about a slope, for instance, in the exact same way that we would normally. It's the change in y for a 1-unit change in x with one catch. It's not y anymore. It's the link transformed version of y, such as logits or logs. We'll talk about logits in just a second. Then we back transform the predictions from this linear model into probabilities or into counts or whatever they need to be. One other piece to this, which some of you have found out the hard way, right, Vladimir? Fixed effects are no longer determined. So in the models that we've seen up to this point, in terms of maximum likelihood searching for what answers make everything the tallest, it only had to search for parameters in the model for the variance. What should the random intercept variance be? What should the random slope variance be? What should the covariance be? What should the residual variance be? And once it figures that out, there's literally a formula by which all of the fixed effects just are computed. They don't have to get found. That is no longer true in generalized models. They get searched for iteratively. So that means models that have lots of fixed effects can take a long time to estimate or may fail to converge. It's not just the random effects that we have to worry about, it's everything. Okay, how are we doing so far? Zoomers?
Is the ML algorithm multi-level and not machine learning?
Maximum likelihood is what
Okay.
ML stands for. But yes, you're right. That could be multi-level. It could be machine learning. It could be lots of things. Yes, meaning the process of trying to figure out what model parameters make everyone's data collectively the tallest. Most likely. Okay, other questions or comments? So this is big picture, conceptual. Let's be a little more specific. So if I have a binary outcome, what I'm trying to predict is the probability of a 1. That's the conditional mean of a binary outcome. So that means the conditional mean has more possible values, right? It's a continuous range between 0 and 1 that we are predicting. So if we try to just throw a regular regression model at this, a general linear model, then what y is, actual y is 0 or 1, but what we're trying to predict with the model is the probability that any one person has a value of 1 instead of 0. So we can do that with the standard linear model, and we have our residual at the end of it. So beta 0 would be the predicted probability of a 1 when my predictors are 0. The beta slopes would be the change in the probability for a 1-unit change in the predictor, and then E would be whatever is left over. Well, what could go wrong? This. A line keeps going. So if I have a predictor that has a positive slope, for example, and it doesn't understand, if I use a standard regression model, that it can't keep going, it will. So I can have predicted probabilities of 1.2 or negative 0.2, and they make no sense. I used to think that binary was binary, but there are many, many examples in the world where even when we think of it as binary, it's not really. Like my round with COVID in August. COVID tests, right? Positive or negative, you would think. No. Here's another dimension. How quickly does it turn positive? How pink is the line? Right? Like there's sort of more to the story than just the binary. So if you think about like propensity to be a 1, then this kind of makes sense. But once you've decided that you're COVID positive, like the line shouldn't keep going. Likewise, COVID negative, like how, is it really, really there? Or is there like a tiny, tiny faint line? Like, it's hard to tell sometimes. But what we need is something that looks like this. We need a model that understands that the highest the probability can be is 1 and the lowest that it can be is 0. So the lines need to bend into this S shape, or what is known as a logistic curve. So here's how we do it. Barbie pink. Yeah, if your COVID test is Barbie pink, you are in trouble. That's what I learned. It needs to be more like salmon and like a very, very pale, like pastel salmon. Then you're less positive somehow, but you're still sick and you should stay in your basement until you feel better. That's what I learned. Okay, so step 1, rather than predicting the probability of a 1 directly, we're going to transform it in 2 steps. The first is to change probability into what is known as odds. So we have the probability of a 1 in the numerator divided by the probability of a 0 in the denominator. And even though this is in fact a ratio, this quantity is not an odds ratio. That is a different thing. And that tripped me up for a very long time. This is called odds. So if I have a probability of 0.7, then odds would be 0.7 divided by 0.3, and that translates into 2.33. If it were the opposite, if I had a probability of 0.3, then the odds would be 0.4. So odds is a metric that stops at 0 and ranges from 0 to up to positive infinity. So that's not better yet. It's not better enough because we still have a boundary on the lower side. Some genius figured out that if you take the natural log of this odds, then the whole thing is continuous. And so that is our new friend, the logit. It's also known as log odds. Whichever of those you prefer, take your pick. I've heard various pronunciations of logit. I had one of my graduate students at Nebraska tell me that because you take the log, it should be the logit. I can't argue with that. That sounds legit to me. I've heard logit, like with a stronger G, logit. Can we take a vote? I'm going to say logit. Logit, or is it log odds? Like in sociology, I've seen log odds more. I'm like, no? Logits?
I mean, I feel like I hardly ever see anything like that talks about like the log odds.
Okay. So yeah, log odds and
It's weird
logits.
because all of our outcomes like fall into the generalized
Yes.
layer of things.
Yeah, generalized models are much more common in certain fields. Health.
So we can hear you. Even microphone. Okay.
Webcam. 1 second. Okay, we're back to good, I think. Okay, lesson learned. I will not touch my computer anymore. My little extension cord thingy always falls out, and that's where all my connections go to shit. Okay, so we voted. It's logit. Okay, so logit is a link function. Its job is to take predicted probabilities and stretch them out into infinity so that we can predict them with a linear model. So the linear model can keep going forever and ever and ever. But when you back engineer that down to probability, the probabilities stay bounded where they're supposed to. That's what it's for. So which type of link function you would need is dictated by what kind of boundaries you have. Logits are used for things that are bounded on both sides. So binary variables, an obvious choice, also proportions. Several of you in your projects or your homework 4 wrote that you have things like rate, like graduation rate, or infection rate, or things like that. Guess what? Rates also can't go above 1 or below 0. So logits are used for those types of variables as well. So here's a mapping of probability on the y-axis to logits on the x-axis. So you see the bendy curve here. Logits can keep going forever and ever, but probabilities stay bounded. And the cool thing about logits is that a logit of 0 corresponds to a probability of 50-50. And the logits are symmetric about 0 in either direction. So if I know that the probability of something happening is 0.9, that corresponds to a logit of 2.2. The opposite of that, a probability of 0.1, corresponds to a logit of negative 2.2. Probability of 0.99 corresponds to 4.6. And I have here, can you guess what the probability of 0.01 would be if I finish the table down here? Yeah, minus 4.6. It's symmetric. Now, this is a big deal because what is going to happen in the models that we see, some software is going to predict the probability of a 1, and some software is going to give you the probability of a 0 instead. But you can always get back and forth by multiplying by -1. So if your software gives you the probability of a 1 and you want the 0, flip the sign, and vice versa. Here's a better picture. I like this one because it shows how changes in logits correspond to increasingly smaller changes in probabilities. So we can talk about a slope in logits the same way as usual. It's the change in logits for a 1-unit change in x. But we cannot talk about a slope directly in terms of a 1-unit change affecting probability, because the change in the logit corresponds to increasingly smaller changes in probability. So a probability of 0.5 is sort of the neutral point here on this, corresponds to an odds of 1, meaning 0.5 divided by 0.5, and then the natural log of that getting us to the logit is 0. So 0 is the neutral point for these variables. So that's one problem fixed. So the purpose of the link function, logit in this case, is to take our predicted outcomes and make sure they stay within their boundaries. Then we have this deal with E. If I fit a regular general linear model, I'm saying E has 3 characteristics: independent, normal, constant variance. Well, independent we know how to fix, right? Right? Like that's this whole class, right? What do you do if people are dependent, meaning related? Add random stuff, yeah, because then the random stuff lets them be related. It predicts the correlation between the people as part of the model. So we're going to fix that one subsequently. But what we have not fixed as of yet is the last two, normal with constant variance. Well, if I have a binary outcome, each E can only be one of 2 things. Like I have a predicted probability that's here, and either I'm wrong by that much or I'm wrong by that much. There's only 2 values for each one. So there's no possible way that the residuals could be normal. And how wrong I am, and my capacity to be wrong in terms of misprediction, is highest for a probability of 0.5, and it shrinks as you move towards the boundaries. So variance is not constant either. It can't be. The variance around a predicted probability shrinks as you move closer to the boundaries. So we need some other distribution besides normal, because normal says there's only one variance and it's constant no matter what the predicted outcome is. Well, there's an app for that. We have a Bernoulli distribution we can borrow instead of normal for our conditional. The Bernoulli distribution is the simplest one. It's the probability of a 1, if that's what you got, or the probability of a 0, if that's what you got. The end. It has only one parameter to it. It doesn't have variance. Because if the mean is 0.25, I know how many people had to have gotten a 0. That's the only other possibility. And likewise for the other choices shown here. So what's going to happen when we predict binary outcomes is that the idea of E at the end of the level 1 equation, it's going to go away. Not because the predictions are perfect, but because it's not an estimated quantity anymore. It is determined by the mean. It's tied together. So our new model, fixing both problems at once, fixing we want to keep the proportions within boundaries, and fixing the E can't be normal problem, is what is known more commonly as a logistic regression. So the new outcome that we're predicting is logit Y, which looks like this. It's the log of the probability of a 1 divided by the probability of a 0, or written here 1 minus the probability of a 1 instead. That whole nasty thing is a logit. But the good news is that if you're predicting logits directly, the rest of your model looks pretty standard. Beta 0, can you guess what that would be? What's an intercept? Yeah, it's the predicted outcome when the predictors are 0, predicted logit outcome in this case. And beta 1, for every 1 unit change in x1, logit Y goes up by that much. So I like this. This is what I prefer to do, because I like the linear model as it is. You just have to handle the fact that you're predicting logits. So then you get back predictions of like a logit of 1.5. Well, what is that? And that's where the problem comes in. What I can tell you about a logit of 1.5 is that it's above a probability of 0.5, because a logit of 0 is the neutral point. So that means they're more likely than not to have a 1 if their predicted logit is 1.5. But if you try to like make a predicted, like a picture of predicted outcomes and the y-axis is logits, but people are like, what the hell is that? Like that doesn't translate into anything useful. So then people try to, okay, well let's simplify it a little bit on the y side here, and let's turn this thing into odds. So if we take the log off of it, unlog it is the way that I say that, although I believe that the correct term is not that. Any mathematicians want to give me the correct term? Exponentiate? That was going to be my guess, but I didn't want to be wrong. Okay, so we unlog it by exponentiating. So e to the linear model is what we end up with. And if you were to take the e and distribute it across, it ends up that these things multiply each other instead of get added, and I can't handle that. That breaks my brain. So then we're sort of in the middle where odds are useful, and you will see that a lot in a medical context. Like people will talk about odds and odds ratios and odds of happening if you're in this, treatment condition versus the control condition and that kind of thing. Well, if you're going to make it the most understandable in terms of a predicted outcome, we got to go all the way down back to probability. Because if you put probability on a y-axis, people will know what that means, right? 1 means absolutely certain, 0 means not a chance. But then you have this thing. It's like, what do I do with that? I cannot talk about this in any sort of typical linear model way. And for those of you who are planning on taking IRT in the spring, it's always going to look like this. That's how IRT models are written, and that's why they look so damn weird relative to other things, is because they're written to predict the probability of an item response rather than the logit of an item response. But guess what, folks? These 3 are equivalent. They're different ways of saying the exact same thing on different scales of the outcome. And this equation is also the same thing. The difference is the -1 in here. So in my Excel calculations and in some of my formulas in R, for instance, I write it this way because it's less typing. That's the only reason. So all 4 of these are equivalent. The last 2 predict probability directly, this is logit directly, and this is what's estimated in the model. So the top one is what's actually happening in terms of the software. The rest of these are transformations of that process. And this is our friend, logistic regression. So link function here, this is the inverse link, to go from logits back down to probabilities. Okay?
Oh, I was just doing the math
Doing the math.
in my head.
Yeah. What did you learn?
These are equivalent, and I was like, okay. Yeah, they are.
Well, it's not because I figured out the math. It's because people smarter than me figured out the math, and I'm copying them. Like, I trust people, right? You know?
I believe you. I was just like, in my head, is that making sense to me?
Yeah, it doesn't make any sense to me. I can't work with this. Like, this is the only thing that makes sense to me, and I'm okay with predicting logits. So where things go sideways is what you can transform back down to probability and what you can't. So I have a table about this with the matching of the terminology and how we talk about these things. So let's say that, hang on, this is going to bug me. Conditional got shoved over in my little picture. That's going to bug me. Conditional. There, that's better. Thank you. All right, so if this is my model, predicting logits directly, the conditional mean that I get back y hat here. Is the idea of what this end result ends up being as a number. And it's in logits. Cool. So I can take that predicted logit and exponentiate it, and that becomes odds. So what are the odds of a 1 relative to the odds of a 0? If I then go all the way down to probability, then I can talk about e to the logit over 1 plus e to the logit gives me the predicted probability that's implied here. This is all kosher. So any one of these 3 could be your y-axis. They're just different ways of saying the same thing, and different audiences might find one of these more useful than the other. Nobody finds logits useful but me. The slopes, though. The slope in logits is nice because you can talk about it as if it's a usual linear slope. Change in y for a 1 unit change in x, so long as you say logit y. A commonly used effect size for these slopes is an odds ratio, which is what you get when you exponentiate the slope. So all software packages will spit this out, or it's very easy to do with just a transformation function in R, for instance. But here's where the problem comes in. You cannot take a slope and talk about it in terms of change in probability. It does not work. So you can only go down to probability in terms of the predicted outcomes that are created by the slopes. You cannot take the slopes down with you. So the order of operations that you would have to follow is you use your logit slopes to build a conditional mean y hat here, and then you take that predicted mean and turn it into a probability. Order of operations. So that's what we'll do. Okay, I don't want to do the next thing yet. How are we doing? Not yet. Okay. Do you want to see an example? Yeah.
So whenever you're writing results sections, do you go back and forth in the language that you use to describe it? If you when you talk about something in probability, do you start off with, the conditional mean and probability, then go to odds ratios or logits for the other slopes, or do you just try to stick with one consistently?
I mix it up. So the question was, if I'm talking about these things, how do I do it? I can give you an example. The 19-page handout that I finally finished this morning, because I cannot leave well enough alone, and that is going to be the death of me. Let me get to the part where there's words.
Didn't we just start this class about perfectionism?
Yeah, we did. Your point? Do not do as I say, or do not do as I do as I say. So here's an example. This is the binary section here. So we're talking about, for instance, the fixed intercept of the outcome that I have was this in logits, negative 1.172, which corresponds to a probability of 0.236. So I start with what does the model say, and then what does it mean? And then I'm talking about so dense down here we get to the fixed intercept was this, which corresponds to this probability. The slope of this predictor was 1.443 in logits, which translates into an odds ratio of this. So that's how I do it. But I think that if you have a table, you can have a column of logit estimates and their standard errors, because those are all in logits, and then another column of odds and odds ratios. And if you want to, you could have a fourth column of probabilities, but only for intercepts or other kinds of predicted values. You cannot take a slope and talk about it in terms of probability. Okay. So let's go to the top of this here. Now this is probably, theoretically, the dumbest example that I've ever built, so I'm just going to ask for your forgiveness. We're going to predict who gets free lunch from math, because that's the only data that I had, that I knew well enough to build a complicated example out of. So if you can forgive the completely backwards nature of this, then it's an example of how to predict a binary outcome. But this is essentially the inverse of example 4, where we were taking free and reduced lunch and predicting math. So at least you're familiar with the story and the circumstances of these real data from a Midwestern rectangular state. So this example has, well, that doesn't narrow it down. There's many that could be called that, or rectangular-ish, right? So we're going to have binary, where we're collapsing free and reduced lunch into one. I got an ordinal example where we don't collapse, and then my attempts, as I said, my attempts at nominal. That should tell you right away how well that went. And SAS, data R, and I also threw an M plus in there, because M plus was the way that I knew would provide full information maximum likelihood for sure. That's available in these two programs. It does not appear to be available in R as near as I could tell. So example time. So you're familiar with these data already, but because I want each handout to sort of stand on its own, I replicate things. So here's my lunch variable. 69% of the kids in this sample got no discount, paid for lunch. 8.7% had reduced, and 22% had free lunch. Okay. So usual descriptive things. I'm not going to do the predictors yet because we're not going to have time for those probably. We have, let's see, yeah, skip that, skip that, skip that. Usual stuff. Okay, first thing, logit model. The first model that I'm going to fit here is not a multi-level model. It's an empty model assuming no cluster dependency. Now, why would I do that? Figure out whether the software is predicting the 0 or the 1. That is exactly right. This is not just for pedagogy. This is literally checking what is happening under the hood. Not all software has technical documentation that is readily available or readable, quite frankly. Some of it's just scary, and some of it's not there, such as in R. So this is my way of figuring out what the software must be doing, because I know the right answer. I know that this variable right here, so in the binary models, I've collapsed 1 and 2 together, so free and reduced lunch is one category, and I know that 30.75% of the cases have that. That's the number that I should get back if the model is predicting the 1. If the model is predicting the 0, here's the number I should get back. So level 1 is written like this: the log of the probability that this variable is 1 over the probability that this variable is 2. And by the way, I've named this variable lunch2, which means 2 categories as opposed to 3. So all I have in the model right now is this fixed intercept. That's it, 1 parameter. And down below, I've started labeling things. G means gamma. So like down here, I have GOO in logits to try and help us figure this out. So first in Stata, I'm using ME logit, even though there's no mixed effects in this model. This is all the code you need. No log just shuts off like iteration history from clogging up the output. And my coefficient is this, negative 0.8. Now what scale is that thing in? Logits. It's negative. What does that mean?
Below 0.5?
Below 0.5. Now, how much below 0.5? I don't know. I don't have it, like, I could guess, but I know the answer because I made the handout. So we'll just look at that. So how do I take this logit and turn it into probability?
Inverse link function?
That's the term for it. Inverse link function is right here. E to the logit over 1 plus e to the logit. Corresponds to a probability of 0.3075. Ding, ding, ding. That means my model is predicting the 1. In Stata, I asked it to do that by adding a statement called NLCOM, which I believe stands for nonlinear combination, as opposed to linear. That's what I would guess. That means you can do all kinds of crazy shit like exponentiate and stuff like that. The only catch is that you have to figure out what Stata has labeled your parameters as. And so there is an option coef legend that I had to add to figure out what it called the intercept, and this is what it called it. So Stata's internal label for that logit intercept is right here. It is an option, let me write it on here, coef legend, I believe. That works in all the models. I have that in comments in several of the things here because I had to figure out what stuff was called before I could use it to do math. So this is the shorter version of the inverse link formula, 1 over e to the not logit. So negative 1 in here. Note that. That's what makes it the shortcut formula. That is, where'd it go? That is this version right here. That's what I wrote out because it's less typing. So I asked Stata to convert this logit into probability, and that's what I got. And it also gives you things like confidence intervals, so those are helpful too. Okay, with me so far? Our folks, I am using GLM, which stands for Generalized Linear Modeling, not General Modeling, although it will do General Modeling as well. This is a base R function, so nobody's special package. Family is binomial, link is logit. So Bernoulli is a distribution that is a special case of binomial for one trial. So binomial is a more general term, but that's also what you would use for modeling rates and proportions. And formula, lunch 2, squiggle 1, only the fixed intercept. And then I just need to ask for a summary because it already gives me -2 log likelihood. It labels it as residual deviance. There's a reason for that, but I don't need to tell it to you because it's not relevant right now. That's what it is. And again, I know that because I go to my other packages and I'm like, is that what it is? Okay, that's what it is. There's a lot of detective work that goes into building these things. So this is in logits. If I want to take it and turn it into probabilities, then I can access the stored coefficients, and each package stores things a little bit differently, so it takes some trial and error sometimes to find something that works. But this, I'm able to do coefficients from model 1 as the object that is stored, and then do the same, not the logit, -1, so that I get the probability. And that should have, by the way, a G-O-O in logits. There we go. There. So that's not so bad, right? Do you want to see the multi-level version? Like an empty model? Because we did a couple of those earlier in the semester, and I just sort of waved my hands at it. So this is the put the hands down and actually explain it section of the program. So we added our new friend, U0 here, random intercept. ME logit lunch 2, now school ID is here. Implicit after it is that an intercept is being estimated that varies over schools. And int 0.7. That's an estimation option. We haven't talked about that yet, but what that refers to is 7 quadrature points, for those of you who are familiar with marginal maximum likelihood. That's the default in Stata. This is one of the reasons why you can get different answers across different packages as to what they default to with respect to their estimation. We'll talk about that later. So we have a new logit intercept. It used to be -0.8, and now it is -1.17. That's a little weird. It has a different interpretation. It is now the mean of the cluster means, but in these models, I actually have to go further than that. This coefficient is what is known as a unit-specific coefficient. It is not just the mean of the cluster means. It is the mean specifically for a cluster that has a random intercept of 0. It's conditional on the random effects, beyond just being conditional on any predictors being 0. So it's not really the mean anymore. It's closer to the median, actually. I have a reference, is it on this page? I think it is. Yeah. Here's a couple books that I would recommend that cover generalized linear modeling from a mixed models perspective, and they both talk about the idea of unit specific. But what it means is that it's specifically for a cluster that has a random intercept of 0. So if I had started from here with my random intercept variance in the model, then I wouldn't get the right answer back with respect to the predicted probability of a 1 or a 0. It wouldn't match. So that's why I started with an empty model without a random intercept, so that it would replicate the mean of the variable one way or the other. So here's my random intercept variance. That's the extent to which the propensity to get free lunch, we'll call it that, varies across schools in logits. Now what's not here? That's usually part of my output. Residual variance. Where'd it go? Did I forget to paste it in? Yeah, it's conditional on the mean, so it's not a single estimated quantity. It's gone. You're not going to see it. It doesn't mean the model's perfect. It doesn't mean there's no residual. It just means that we don't need to estimate its variance, because once we figure out what a predicted probability is for each person, we know what the variance around it has to be. And it's not constant. So if you try to make like prediction confidence intervals, They will be widest around predicted probabilities of 0.5, and they will gradually shrink as you move away from that. So that's a bit of an issue if I want to compute, say, an interclass correlation. Well, the formula has residual variance in it, and I don't have a number for that. So what do? The answer, as arbitrary as this sounds, is you put in 3.29 for the residual variance. Yes, those looks are correct. What? Did you just make that up? Not exactly. The actual number that I'm putting in is pi squared over 3, where pi is 3.141 blah, 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 blah. I only know 3 digits of pi. That's how you know I'm not a math person. I could be a physicist. I actually could not be a physicist. I'm very, very bad at physics. I took it in high school, and it was very, very hard for me. And then I studiously avoided it throughout college. So. Yeah, it came back to bite you, though, didn't it, right? Statistics is fun. Statistics is not math. It's programming and logic. You can do programming and logic. It can't do math. Well, the good thing is that the computers do the math. We don't have to do the math. So where the hell did that come from? You might be asking yourself. The answer is this. So this is a picture I stole from Wikipedia as usual. But I've started adding citations for my stolen items so that, it seems more fair. So this perspective is thinking about logits as a continuous entity. And the logic that goes with it is, I know that you have this binary outcome that you've observed, but what if underneath it there's actually a hidden latent outcome that's continuous? And somebody just chopped it up, and that's what you ended up with. So from that perspective, what these models are often described as saying is that the underlying continuous distribution that we're representing in logits actually is logistic in shape. So the propensity to get free lunch, if you can think of it as continuous, or how COVID positive are you as a continuous variable, as an underlying variable, indicated as the size of the pink, the amount of the pink. Chris says, you didn't have me as a teacher. I did not. Maybe I would like physics better if I had someone else as a teacher, although that teacher wasn't terrible, as I recall. I'm just really bad at things that involve spatial reasoning. I am. Anyway. No. You're in Coralville, somewhere off the strip. That's all I know. So logistic distributions look like this. And the mean invariance of the logistic distribution, it's pi square over 3 times a scaling factor that automatically is 1 if we're talking about binary outcomes. So that's where that number comes from. It comes from the belief that if I had an E, its variance would be 3.29 because my E is in logits. And I'm assuming that E's distribution is this logistic distribution that looks an awful lot like normal in most of these cases. But it's not. It's more pointy. So it's not as arbitrary as it seems. So what's going to end up happening is that anywhere that you would do a residual variance as an estimated quantity, we're just going to throw in 3.29 instead. That is what we would throw in if we're using logits. So in Stata, you can ask for, does it do the interclass correlation? Yes, it does. It does for binary, it doesn't for ordinal. So Stata, you can do stat.ICC, and it'll spit out an ICC, and that's where that number came from, is by using the random intercept variance that it estimated divided by that plus the residual variance placeholder of 3.29. So in logits, the intraclass correlation of this free lunch variable is 0.373. In logits, we can't forget that part. There really is no way to talk about ICCs in terms of probability. Because when you go back down to data scale, what this residual variance would be would depend on where your prediction is, right? It's not constant. So there'd be a different ICC at every predicted probability. So this is in logits. So in logit Y, 37% of the variance in free and reduced lunch is because of what school this kid goes to. So I can go back and predict the intercept. In this case, in probability, it's 0.236. So for a school that has a random intercept of 0, the predicted probability of any one student getting free lunch is 0.236. In R, I skipped down to R. There we go. In R, I am using, and I'm going to call this Glimmer. And I will not accept any arguments on that. It's Glimmer. Okay. I suspect they did not mean it to be Glimmer, but that's what it looks like to me. It's Glimmer and Go Logit and fun things like that. So Glimmer looks a whole lot like Elmer, except for this part, which is putting in the right link function and conditional distribution, and this thing right here, which is number of adaptive Gaussian quadrature points. That's what AGQ stands for. Gaussian means normal. We'll talk about what that means later on. But I'm controlling this so that I get the same answers as Stata as close as possible. And it's the same answers out of SAS, by the way, too. So in R, Glimmer, the syntax for the model looks exactly the same otherwise, not different at all. R will give you intraclass correlations, and it's using 3.29 as the residual variance as well, so the answers agreed. And then you can ask it to unlogit back down to probability, your predicted intercept, and other than coefficients, turns into fix F. Because why not? Why would it be the same? You got to keep you on your toes. Intraclass correlation significance test. In Stata, it's given by default. So the same LR test versus logistic model, that's testing the addition of the random intercept variance. Chi-square statistic of about 3,000, so yeah, we'll say that's significant. And R wouldn't let me use Renova. Renova is only for Elmer, it told me. And I was like, well, I have a log likelihood. I asked for it. It's right here. So can I just do it myself? Sure. So that's what I did. I got tired of fighting with R, and I just did it myself. So I computed a new object called dev test for deviance test, -2 times the log likelihood from the single level model, minus the log likelihood of the empty model for, yeah, whatever this is called. Model 2. This is not right. Hang on. This is a copy-paste error. That's what that is. And let me fix it. Model 2. And model 1. Always fewer minus more in the order, by the way. Smaller model minus bigger model. There, now that works. I get the same answer anyway. Last but not least, 95% random effect confidence interval. I can do that still too, just that it's in logits. So I can take the logit fixed intercept plus or minus 2 standard deviations as given by the random intercept variance. That works out to a confidence interval. 95% of my schools have predicted logits that range from this, and because these are predicted logits, I can take them all the way back down to probability. So somewhere between 2% and 83% of the kids in a school are going to get free lunch. That's the range. It is, but and this is allowed because these are predicted outcomes we're talking about. Intercepts are predicted outcomes. So you can go from logits to odds to probability, no problem. Okay, so that's not bad, right? I'm sorry, but I have to make it worse. Can we do that next time? Yeah, maybe. I don't have to make it worse yet. I know. I don't have to make it worse yet. I can skip this for now, but this is coming. Thresholds and intercepts are coming. I know. Odds ratios. So odds ratios as effect sizes. We can talk a minute about that, maybe. So an odds ratio is a ratio of 2 odds. I know, it sounds like gibberish. But this is what it would look like. So this thing right here, that's odds. So I have a predicted odds of a 1 given my model, and I can talk about how the odds change as a function of my predictors. So for instance, if I have a binary predictor, so x1 is binary, then an odds ratio is built like this. It's the probability of a 1, given that my predictor is 1, divided by, see there's a division sign here, the probability of a 0, given that my predictor is 1. So the numerator is, okay, if x1 is 1, what's your odds? The denominator is, okay, if x1 is 0 instead, what's your odds? And so the odds divided by the odds divided by the odds divided by the odds is the odds ratio. It's like 4 things. I'm going to be honest with you, I hate these. I hate them with the fire of 1,000 suns. Why do I hate them, you ask? Maybe you don't want to ask. I'll tell you why. They're asymmetric in a way that bothers me. And Chris, we've been over this. I understand that between 0 and 1 is just as many numbers as 1 to infinity, but I don't like it. They're asymmetric. So if I have a slope of 1 for this binary variable, the odds ratio that goes with it is 2.7. So odds ratios, the neutral point is 1, meaning your odds of something happening if you have the predictor are the same as your odds of something not happening if you don't have the predictor, right? Break-even point. So if I have a positive slope, that corresponds to an odds ratio above 1. And the odds ratios range from 1 to positive infinity for positive slopes. Well, what if my logit slope is negative 1? That's just as strong, right? It's just the opposite direction. It means that the logit goes down by this much for a 1 unit change in x. Well, then the odds ratio has to stay between 0 and 1. And for negative slopes, it's going to be between 0 and 1, such as this one, which is 0.37. So these are equivalent effect sizes. It doesn't look that way, though. That's what bothers me about this. The positive slopes get to spread all the way out to positive infinity. And Chris says infinite numbers both ways. I know, but it just doesn't look like it. And negative slopes are trapped between 0 and 1. So I feel like intuitively it's harder to get a sense of how big a negative slope is because they just seem much more compressed. The other reason that I don't like these is because of a unit. So what if you have predictors that are binary, right? Those are all comparable in terms of what a unit is. It's a switch from not having something to having something. But what if you have a continuous variable? Well, then is your unit 1 unit change? 10? 100? That changes your odds ratio. Even though it's the same information, it's just being rescaled. So if you want to talk about different predictors in a model and compare their odds ratios as indices of effect size, you can't do that if they're not on the same scale. So it's really not an effect size in the sense that effect sizes are supposed to be standardized so that they're always comparable. They're not. And that's why I hate odds ratios.
Wait, can you explain that part again?
Yes. So an odds ratio is tied to a unit, a 1 unit change. If you have a continuous predictor, a 1 unit change does not mean the same thing as a binary predictor of a 1 unit change. So your binary predictor odds ratios may look way bigger because you're talking about like a change of all the information in the variable as opposed to $1 or 1 degree or 1 more item, or like what does 1 mean? Yep. So I think it's harder to compare effect sizes across predictors because they're not on this, they're not standardized. So that's why I hate odds.
So is there like an additional step you can do?
There may be, but I'm not aware of one.
But it must not be that easy or common or frequent.
It's not that common from what I understand, but most of the literature that I read is focusing on continuous outcomes. So I don't see as many examples of that. So,
Would be that a lot of the variables that go into the model are also like some sort of binary predictor thing, and so
yes.
it's probably not as common.
Yeah, if everything is a categorical predictor, everything's a dummy code of some kind, then it's more fair. But if it's a 1 unit change in a continuous variable, then it's not comparable. All right, no, we're not doing that. Okay. So why do people need to do odds? it goes back to this. E is not here. So if I have an empty model and I haven't explained any within cluster variance, what's my level 1 variance? Where's the picture? 3.29. What if I build the world's best, most strongest predictive model? I absolutely can figure out what the probability is based on student characteristics. What's my residual variance? 3.29. So can I do any kind of R square anything? No. So you're stuck with it. What's going to happen is that as we add predictors at level 1, in order for the residual variance to still be 3.29, the rest of the model has to change scale to have it be what would the scale of the total variance had to have been to still have 3.29 left over. So coefficients change scales across models, and they're also not comparable for that reason. But that's not a multi-level problem. That's a logistic regression problem. That's a generalized problem. And we'll see examples of that next week, because it's time to go. All right, any other parting questions? No. Then thanks for being here. Hopefully next week will be a little bit better. Because we've had like the hard part, right? Logits, 3.29, we'll get there. All right, let me know if you need anything. Have good weekends, do your formative assessments. See you later. Bye, Zoomers.